Hi, and welcome to this video on forces, specifically Newton's second law. So at this point, you should have done a lab or seen a video where we talked about an object undergoing accelerated motion. For this class, it is typically a cart on a track. And as a force is applied to the track, it starts moving to the right, moving this way with increasing speed. And this takes us to Newton's first law, which states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an outside force. Or, in other words, if there is an unbalanced force, there will be an acceleration. If there is no unbalanced force, there is no acceleration. In this case, we have an unbalanced force. This force applied by a fan or by your hand or whatever. There are plenty of people who abbreviate this as force applied. Typically, we'll be a little more specific, stating what is applying the force. In this case, the fan on cart. And it accelerates in that direction because it's not opposed. We do have two other forces we do need to talk about. We have a normal force coming from the track, stopping from going down. And then we have our gravitational force pointed into the earth. And while the object is accelerating, it's not accelerating in the up-down direction. If you think about a car driving down the street, or in this case, the cart moving down the track, it's not moving up or down, it's only moving left and right, which tells you that these forces must be balanced. So, at this point, there is an unbalanced force, so there will be an acceleration in the direction of the unbalanced force. In other words, the object will accelerate this way. Let's put that down. And at this point, we've done some experiments. We've noticed that as the force increases, so does the acceleration. So force goes up, acceleration goes up. We also have done some experiments where we notice that as the mass goes up, acceleration goes down. Put these into math terms. Force goes up, math goes up. That means force is proportional to acceleration. This is the symbol for proportional. And since as mass goes up, acceleration goes down, this could be mass is proportional to 1 over acceleration. Or how we will typically say this is 1 over mass is proportional to acceleration, just flipping those over. As one goes up, the other goes down. This inverse relationship is typically how that's done. Putting these facts together, adding them effectively, we get a relation that is often known as Newton's second law. It states that acceleration equals force divided by mass. But the more common way you'll see this is force equals mass times acceleration. Little hats to indicate vectors, points in a direction. The force is to the right, the acceleration is to the right. But this is non-specific. We need to be a little more specific about what we're talking about here. So let's take this situation here and examine it a little more closely. Because if force equals mass times acceleration, then there should be a acceleration up and acceleration down. So we need to clarify. So let's take that F equals ma and put it into more specific terms. Specifically, we use this little symbol here, this sigma. And what this tells us is that the sum of all forces, or the also known as the net force, equals the mass of the object times the acceleration of the object or system. The net force acting on an object equals the mass times acceleration. In this case, the normal force and the gravitational force cancel out. So whatever force you're applying, the fan on the cart, for instance, will provide your acceleration. This allows us to start talking about some fairly simple ideas. Let's start with this one. If this cart has a mass of 0.25 kilograms and is experiencing a force of 4 newtons, what's the acceleration? Well, net force equals mass times acceleration. In this case, the normal force and the gravitational force aren't particularly relevant. We'll talk about them more later. But my net force, the only force being applied on it in a direction, is my force applied. If you don't believe me, what you can do is we can copy this over, and we notice that the up and down just cancel each other out. They have no effect. It ends me back here. So I can find the acceleration if I know the force and the mass. So 4 equals mass 0.25 times A, or A equals 16 meters per second. Pretty simple. But let's talk about how it gets a little more complicated. So instead of talking about the fan cart, let's talk about a slightly different situation. Imagine you have an object, a box sitting on a table. You push on the box to the right, and friction stops it from moving. There's no acceleration. The forces are balanced. Gravity is pulling it down, and your normal force is up. If we take a look at this, we move our arrows around. We see, as we move our arrows, we end back up where we start. There is no net force. We have no acceleration. This matches with what we know, and it shows the math is consistent. Let's take it a step farther. Instead of the forces being balanced, imagine you push with a force greater than the frictional force. The box starts to move. And in this case, your forces are no longer balanced. You have an imbalance. So we take our forces, we add them. We can add them as vectors, like so, visually, or we could do it mathematically. But the point being that instead of having everything add up to 0, end up back where I start, I have this leftover amount. And this leftover amount here is my net force, or my sum of all forces. And that amount, whatever that force amount is, will tell me what my acceleration is, what my mass is. So let's put some numbers to this. Let's say that my normal force is 50 newtons. My gravitational force is 50 newtons. My force applied is 75 newtons. And my frictional force is 25 newtons. Nice numbers to get this going. In this case, there's a clear imbalance. Up and down are balanced, but left and right are not. So in this case, which side's winning and by how much is how I typically will think about it. Well, up and down are balanced, so it's not up and down, but left, right, or not. It's 75 newtons to the right, 25 to the left.
75 is 50 bigger than 25, or in other words.
So my net force, or my sum of all forces, is 50 newtons to the right. Okay. So let's take this a step further. If this is a 5 kilogram box, what's the acceleration? Well, F equals ma. Okay, my net force is 50 newtons to the right. My mass is 5. So my acceleration is going to be 10 meters per second squared. And from here, I can go back and do a kinematics problem. How long does it take to travel the track if it starts from rest? Once I can find the acceleration from my force, I can go back and do a kinematics problem. Or alternatively, I could do a kinematics problem, find the acceleration, and then use that to calculate the net force acting on an object. Both of these are valid. Let's take a look at an example problem. Here we have two sample problems, fairly simple ones. In the left one, I want to know what the net force is and what the acceleration is. And the right one, I want you to add forces to the diagram, interactions, such that the net force on this object to the right will be 0. Go ahead and give it a try. Check back after the pause. Okay, let's take a look at this. On the left one, I calculated the net force. The up-down forces were already balanced, so I didn't need to worry about them. But left and right, I had a 60 on one side, 20 on the other, which means the frictional force in this case is winning or overcoming the tensional force Ft by 40 newtons. So my net force is 40 newtons to the right. Once I have my net force, I can find my acceleration. Net force equals mass times acceleration. In this case, 40 equals 8 times a, which tells me my a is 5 meters per second. The second one, I add forces. All I need to do is add some appropriate forces in this case. So they could be friction, they could be tension, they could be normal force, applied forces, whatever. The important part here is the numerical values. Each force has to be canceled. So I need 15 newtons pulling up to cancel the 15 newtons pulling down. I need the 25 newtons to the left, cancel out the 25 newtons to the right. Left, right needs to be balanced, up, down needs to be balanced. Pretty simple, pretty easy, but scaffolding building forward.
Thanks for watching. See you next time.